Lecture 5.1 Characterization of Nanomaterials. Today we are going to talk about one of the most critical aspects of nanoscience. How do we actually know what we have made? When you synthesize a nanomaterial in the lab, you can't see it with your naked eyes. You can't feel its shape. You can't directly count its particles. So the question becomes, how do we measure, confirm, and understand something that exists at a scale 1,000 times smaller than a human hair? That's exactly what characterization is about. And today we are going to walk through the key properties we need to measure and the most important techniques used to measure them. Let me start with a simple but important point. At the nanoscale, properties change dramatically with size, shape, and surface chemistry. Take gold, for example. In bulk form, gold is yellow and chemically inert. But gold nanoparticles can appear red, orange, or blue depending on their size. They become highly reactive. Their melting point drops significantly. This is not magic, it's physics and chemistry operating at that nanoscale. So, if you don't characterize your material properly, you don't actually know what you are working with. Two batches of gold nanoparticles from the same synthesis protocol can behave completely differently. If one has particles of 10 nanometers and other has particles of 50 nanometers, or if one is spherical and other is rod shaped, their behavior will be different. This is why characterization is not optional, it is fundamental. There are also unique challenges at the nanoscale. Particles tend to agglomerate, meaning they stick together, which affects measurements. Surface also plays a dominant role because the surface to volume ratio is enormous. And the quantum mechanical effects start to appear that simply don't exist in the bulk materials. Before we go into techniques, let's list what we actually want to know about a nanomaterial. Think of this as your characterization checklist. First, size and size distribution. Not just the average size, but how narrow or broad the distribution is. A narrow distribution means all particles are roughly of the same size. A broad distribution means you have a mix which complicates interpretation. Second is morphology and shape. It is important to know whether the particles are spherical, rod-shaped, cubic, or star-shaped, as the shape affects optical, magnetic, and catalytic properties significantly. Third is crystal structure and phase. We need to know if the material is crystalline or amorphous. If crystalline, what is the phase? For example, titanium dioxide exists in multiple phases, anatase, rutile, or brucite, each with different photocatalytic activities. Fourth is surface area and porosity, essentially relevant for catalysts and drug delivery systems. A high surface area means more active sites. Fifth is chemical composition. We need to know what elements are present, are there impurities, and what is the stoichiometry of that material. Sixth is surface chemistry. For materials, we need to know what functional groups are on the surface. Are there capping agents or ligands attached. This determines how the nanoparticles interact with the environment. Seventh, optical, electrical, and magnetic properties. Depending on the application, these may be the most important properties to be measured. Now, let's go through the main techniques which are used for characterization. The characterization of nanomaterials can be presented by this histogram. By going through this, you can outline the basic features, how the characterization of material takes place. The characterization of nanomaterial can be classified in various categories, such as for structural and morphological characterization, we use techniques like TEM, SEM, AFM, and XRD. For size distribution, we use techniques like DLS or NTA. For surface analysis, we use techniques like BET, XPS, FTIR, or Raman spectroscopy. For optical and thermal techniques, we used UV visible or PL, like TGA techniques are used. For structural and morphological techniques, we have transmission electron microscopy, that is TEM. This is one of the most powerful tools in nanomaterial characterization. In TEM, a beam of electron is transmitted through a very thin sample and an image is formed based on how electrons interact with the material. Then we have scanning electron microscopy, SEM. SEM scans a focused electron beam over the surface of a sample and collects secondary or backscattered electrons to form an image. It gives you excellent surface morphology. Then third is atomic force microscopy, AFM. It uses a very sharp tip to physically scan across the surface of the sample and builds a 3D topographic map of the sample surface. Fourth is X-ray diffraction, XRD. It gives information about crystal structure. The X-rays are allowed to fall on the crystal and the analysis of the diffraction pattern obtained gives the crystal structure. It only works well for crystalline materials. For knowing the size of the nanoparticles and their distribution in the nanomaterial, we use techniques like dynamic light scattering, DLS. It is widely used for measuring the size of nanoparticles in suspensions. Then second is nanoparticle tracking analysis, NTA. It is a technique that tracks individual nanoparticles in suspension using laser light. For analyzing the surface of the nanomaterial, the techniques used are first BET analysis. It measures specific surface area and probe size distribution. Then we have X-ray photoelectron spectroscopy, known as XPS. It tells about what elements are on the surface and also their oxidation state and chemical bonding with the environment. Third is FTIR and Raman spectroscopy. Both the techniques are vibrational spectroscopy techniques that identify functional groups and molecular bonding in the sample material. For characterization of the optical and thermal properties of the nanomaterial, we use techniques like UV visible spectroscopy. It measures how much light is absorbed at different wavelengths. For semiconductor nanomaterials like quantum dots, UV visible can be used to estimate the band gap, which shifts with particle size, and this is the quantum confinement effect. Then we have photoluminescence PL. This spectroscopy measures the emission of light from a material after it absorbs photons. It is essential for characterizing quantum dots and fluorescent nanoparticles. Third is TGA, thermogravimetric analysis. It measures the mass of a sample as a function of temperature. As we heat the material, different components decompose or volatilize at characterization temperature that gives the optical and thermal properties. In this way, there are a large number of techniques for characterization of the nanomaterial. Now, choosing the right technique for your specific sample is the key, because no single characterization technique provides complete information about the nanomaterial. So, a combination of complementary methods is always required. The choice depends on the sample state, the property of interest, and whether a destructive or non-destructive approach is needed. In context of applications, let me briefly connect characterization to real-world applications. Like in drug delivery, the size and beta potential measurements by DLS are critical. Particles must be small enough to circulate in the bloodstream, and a stable zeta potential prevents aggregation that could block blood vessels. For instance, in catalysis, BET surface area and XPS oxidation state determine catalytic activity. A higher surface area and the right oxidation state can dramatically improve reaction rates. In electronics and semiconductors, XRD crystal structure and TEM imaging of defects are essential for predicting electrical performance of the sample material. As an other example, in environmental nanotechnology, DLS and NTA help understanding how nanoparticles behave and aggregate in natural water systems, which has implications for both efficacy and safety. To summarize today's lecture, characterization of nanomaterial is about building a complete picture of your material using multiple complementary techniques. We covered morphological tools like TEM, SEM, and AFM. We covered structural tools like XRD. We also covered size analysis with DLS and NTA, the methods like BET, XPS, FTIR, and Raman for surface analysis, and the tools like UV visible and photoluminescence were also discussed in this. The key takeaway is this: understanding what each technique measures, what its limitations are, and why you need more than one. A good nanoscientist doesn't just run measurements. They choose the right combination of techniques to answer the specific questions their materials demands. Thank you. You can find lot of content on nanotechnology on my